Welcome to video 24 on the TTB course. This video is from part 5 of the TTB course. In part 5 we have first introduced a set of TT platforms that can be used to form the basis of a wide range of reliable and safety-related embedded systems. We have then illustrated how some of these platforms can be employed through means of a range of different case studies. In this video, we consider the development of part of a radiotherapy machine for use in a hospital environment. The material in this video summarizes more detailed presentation in the ERES2 book in chapter 24. If you've not yet read this book chapter, I suggest you do so now and then come back and watch the video after reading the book chapter. The video will make a lot more sense if you've already read the chapter. In this case study, we're concerned with the development of part of the control system for a radiotherapy machine. Radiotherapy is a treatment involving the use of high-energy radiation. It is commonly used to treat forms of cancer, and that will be the area that we're focusing on in this study. Our specific focus will be on external radiotherapy, carried out using what is known as a linear accelerator, or a LINAC. A LINAC is designed to focus high-energy radiation beams onto the area of the patient's body that requires treatment. A typical treatment program will involve use of the LINAC daily over a period of days or weeks. In order to understand some of the challenges involved in developing a controller for a radiotherapy machine, we will briefly consider one of the best-known cases in which such a machine caused problems. Between June 1985 and January 1987, treatments involving a computer-controlled radiotherapy machine, the Therac 25, resulted in massive radiation overdoses for 6 people. Professor Nancy Levison from MIT reports on this case in detail in her 1995 book, Safeware. You'll find a full reference to this book in ERES2. In brief summary, it was possible for operators of the Therac 25 system to enter incorrect operating parameters. As the software did not contain self-checks or other error detection and error handling features, the resulting treatments could be applied to patients, in some cases with catastrophic consequences. The first safety analysis on the Therac 25 did not even include software, although almost all responsibility for safety rested on the software. When problems started to occur, it was assumed to be a hardware problem. This study dates from the 1980s, and you may feel its ancient history. However, a report in the Glasgow Herald describes an incident at Edinburgh Cancer Centre in September 2015. In this incident, a patient received a radiation dose that was 100% higher than intended, apparently because of confusion in the way that the required dosage was to be entered into the equipment. The problems still apparently persist. The key international standard in this area is IEC 60601-21. This standard applies to this kind of medical equipment that includes electron accelerators. Only comparatively recently, in 2014, has a new subclause been added to this standard that requires that the consistency, correctness, and completeness of the dataset used by radiotherapy equipment shall be checked by the equipment before it can be accepted for irradiation. It does seem quite remarkable in many ways that this has only been added in 2014. In the case of failure of consistency, correctness, or completeness of the dataset being loaded, irradiation shall not be allowed to commence through this kind of equipment. So our goal in this study is to explore a TT architecture that will help us to meet this requirement. Just before we look at this, it's important to emphasize that this kind of requirement, entering data into a system before taking a safety-related action, is very common in different fields for example industrial control, even automotive control. Inputs are provided to the system, and we need to provide complete checking of these inputs before we take safety-related actions. So the implications of this study are quite widespread. In our case, we're going to look at a radiotherapy machine, and we're going to focus on 4 key components: the LINAC radiation source, the LINAC controller, the dose monitoring systems, and the treatment control panel. So the LINAC radiation source is the source of radiation that's applied to the patient. If this source is disabled, the risk of harm to the patient or operators is minimal, we assume. The LINAC controller, the LINAC-C, is responsible for taking the treatment-validated parameters and controlling the LINAC-RS in the required manner. If it detects a problem, the LINAC-C shall disable the LINAC-RS. Then we have 2 independent dose monitoring systems, DMS1 and DMS2. These are required to measure the radiation dose applied to the patient and to compare this with the required treatment parameters. If either DMS detects a problem, it shall disable the LINAC-RS. Finally, we have the TCP, the Treatment Control Panel. This is responsible for taking the required treatment parameters from the operator and checking them. If the parameters are found to be acceptable, these shall be passed to the LINAC-C and DMS1 and DMS2, and confirmation from each component that it has received these parameters shall be obtained. If the parameters are not found to be acceptable, the TCP shall disable the LINAC-RS and shall instruct the LINAC-C and DMS1 and DMS2 to disable the LINAC-RS2. Our focus in this study will be on the Treatment Control Panel, the TCP. We're going to implement this by means of what's known as a duplicator I/O platform. So our TCP will be designed to operate as follows. We obtain information via the input processor, in this case MCU-B. We perform cross-checks, sanity checks with the other processor, MCU-A. If we pass these initial checks, we echo the input information on a display connected to the output processor, MCU-A, and await confirmation from the user. If such confirmation is obtained via MCU-B and checked, MCU-A generates the required outputs. Please note that power will be supplied to the LINAC radiation source only if both MCU-A and MCU-B are in the normal processor state. So in this design, the outputs of the TCP will be passed to the LINAC controller and to both DMS modules. These are not shown here. We would again perform cross-checks to ensure that the messages were transferred between modules correctly. And such cross-checks would be carried out by continuing the I/O split between the various modules, each of which would involve a duplicator platform. That means that we send information in each case to one of the microcontrollers in the duplicator platform, perform cross-checks with the other microcontroller, and have the other microcontroller send a confirmation message back to the source of the original message. So the original message might come in and say, do X. The first microcontroller would say, I think it says do X. The second microcontroller would say, I think it says do X as well. If the two agree, then the second microcontroller sends a message back to say, I received the message do X. So we continue confirmation through this process with multiple cross-checks happening between the microcontrollers to ensure that we obtain the required behavior. The end result is that this design will include 4 duplicator-based modules for the TCP, the LINAC-C, the DMS1, and the DMS2. In each module, each processor will have individual control of the power to the Linux RS. In this way, with these various cross-checks and use of this duplicator module, we'll have confidence that we will obtain the correct results from this piece of medical equipment. That brings us to the end of this video. Please read Chapter 25 in the ERES2 book before you continue with the course. Thank you for watching.